Okay, it's 5:25, so let's get started. Quite a lower attendance this time. I don't know why, but it's kind of sad because today is the lecture to not miss of all of them. So yeah, don't miss this one. All right, so just a few announcements. PSET 0 is being graded right now. We have 3 questions done. The grader has 3 more to do. So hopefully we'll get those done. Well, that grader will get them done by tomorrow and at most Sunday. And then when that's done, I'm going to release the grades, and they're going to be available on Gradescope and Blackboard. So the official place we're going to be keeping grades is on Blackboard. So if there's a discrepancy, please let me know so that I can make a correction. So just letting you know, we graded, the grader graded questions 1 and 2 and the bonus. Not counting the bonus for the first 2 problems, out of 20, the average was 11.4. So there are some really great submissions and some not great submissions. Seek help on Piazza if you haven't. All right, PSET 1 is out. So if you haven't started it, you're probably going to be in trouble. If you haven't started, start now. And I like literally this minute now, okay? Because we've had some good discussions on Piazza, but probably not as much as we probably should be. So ask questions on Piazza if you don't understand something. PSET 2 will be out on Tuesday. Some really cool problems in there. You'll see that when it comes out. And midterm exam Wednesday. And I'll talk more about the midterm on Monday, unless there are questions about it now. Yeah.
Okay, so my question is, when you talked about most of the grades being on Blackboard, where are the comments for the questions going to be?
Comments are going to be on Gradescope unless I can move them over, but it's weird. The comment system on Blackboard is HTML based, so I have to convert them to HTML in order to paste them in, unless I do it individually, but then that's 85 times 6. Yeah. It's only 510. It's a finite number. So, yeah, it's not that much. But, yeah, they'll definitely be on Gradescope for sure.
Okay.
Yeah. Any other questions about any of these things?
Oh, and
Yeah.
midterm is not going to be, it's going to be based off of the content from Monday as well.
Yes. So midterm will be everything covered in lecture up until the end of Monday's lecture. So it's not going to include whatever we do the first half of Wednesday. That'd be really unfair. Although I could get really evil. Don't give me ideas. All right. Any other questions? Okay. So what did we talk about last time? Or did, yeah, so we were talking about these things called generalized NFAs. And we talked about, first off, what are generalized NFAs helping us trying to do? Yeah, make a regex from a NFA or a DFA. Yeah, so this is for D or NFA to regex. So we actually, not only in lecture at the very end, but also in the help session in the office hours afterward, we actually went through an entire example of, given a DFA or NFA, try to rip out a state in order to make a smaller generalized NFA until you get to this 2-state situation where you have a single start state, single final state, and one transition over. And whatever's on that transition is the regex that you wanted. So let's try to prove this formally. So let G be a GNFA, or as formally as we can. Let Q be its set of states. So we didn't really give a formal definition of exactly how the GNFA is supposed to work, but we can get an intuition of what it would look like. We could have, what are we required to have? A single start state, what else? Single final state, what else? Nothing's going into the start state, right? What else? Nothing leaves the final state, all right, and then what else? We want to get one transition at the end. What's on the transitions? Regular expressions, right? So every transition has a regular expression. So, and what was our process of getting a regex? We wanted to rip out some state and then replace that state with some regular expressions and some transitions. So what states am I allowed to rip out? Anything but the start or the final state. So let's let Q0 be its start state and QF be its only final state. So I'm allowed to pick any state out of the set of states other than Q0 and QF. So let Q be a member of the set of states without Q0 or QF. So just pick any arbitrary state other than Q0 or QF, assuming that it's a valid GNFA. And I'm going to call this state something else. I'm going to call it QRIP. And the reason for that is that we know that that's the state that we're going to eventually try to rip out. Well, is there any restriction on what could be coming into this RIP state or what could be coming out of it in terms of its transitions? No, it could be any valid regex. Is there anything about whether QRIP has a loop or not? No. So let's treat all of those at the same time. So let's say that this is QRIP right here. That's the state we want to get rid of. And let's say that we have a bunch of states coming in. Let's call them Q1, Q2, Q3. And let's say that there are QS of them, or S of them. And the states that QRIP goes to are R1, R2, R3, up to, let's say, RT. Well, I said that all the Q states go into QRIP. And let's give each one of those names, those regexes on those transitions names. So let's call this one R1, that one R2, R3, and then RS for that guy. And I said that that QRIP is allowed to have a loop. So let's say that X is the loop. And I said that QRIP has transitions out to all the R states. Let's call them T1, T2, T3, T. Yeah, notation can be a problem sometimes. All right. Well, let's see. How many transitions am I going to add? How many ways are there into QRIP? S of them. How many ways out to somewhere else? T. So how many transitions am I going to add?
S plus T.
S plus T? S times T. Because I can follow any one of these RIs into QRIP, and then any one of the TJs out to the R states on the right. So I need S times T transitions I'm going to add. So for all, so I is going to go over the Q states, and J is going to go over the other states. So we're going to have QI have a transition. So we're going to add transition Qi to Rj. But what am I going to put as the regular expression on that transition? Well, how did Qi go to Qrep? R sub I. So that's the guy that's going to go there. And then what? Well, could I go around that loop as many times as I like? X star. X star. And then how do I go from where Qrep was to Rj? Tj. Okay? Well, let's see. So here's a question. What if there exists a transition from Qi to Rj already? I didn't handle the possibility that there could have been already a transition there that skipped over Qrep. Well, what if there already exists one? Yeah, just union. Yeah. So the answer is union Ri x star Tj with it. And here's another question. What if there is no loop on Tj? Oh, not Tj. Qrep. Yeah, so it would be Qi from Ri to Tj with no star in between. Are these, so with the X star and that question I just asked, are those two different things? Or do they correspond to the same thing?
But X star is actually resolved to
Empty string.
So once
What thing starred is the empty string? Empty set. So the formal definition is of a GNFA is all undefined transitions are empty set. And so this second question now actually will always be the exact same case as X star from above. So if X, the loop, is non-empty set, then it'll still be X star. But if it is empty set in the case that there actually is no loop there, then empty set star is just the empty string, but that's just what we had before. So the formal definition of a GNFA is that all undefined transitions are empty set. So you can think of it as a complete directed graph, for example, that happens to have labels on its edges. Okay, does that make sense? So we came up with examples in last lecture as well as in my office hours, and the process that I'm doing here is exactly the same, but we're just formalizing it. But it's exactly the same. Rip out a state and see how many transitions that we need to add, and then just fill in the transitions by reading whatever you need to read in, star whatever's on the loop, if there is one, then concatenate with whatever is on the thing that you need to go to. Okay? It's all just simulation. Any questions on that? So I wanted to fill this in because we do need to formalize it a little bit. But any questions about this? Okay, so new topic. And so I'm just going to warn you right now, this is probably the least understood topic in this entire class. So that's why I said this lecture is the most important one. So make sure you're paying attention to this one. Because at the end of today, we'll actually figure out DFAs can't do everything. So there are some problems that there are no DFAs that can actually solve correctly. Well, let me pose to you one sample language. So I want all the strings in 0, 1 star such that W has the same number of zeros and ones. And if I was really, really mean, I'd ask you to make a DFA for this. Why am I mean? Because we'll prove that there's no DFA for this. Well, what if we tried? I claim we will fail somehow, but what if we tried? Well, let's see. I'm going to list off some strings, and I want you to tell me whether they're in this language or not. So, some strings. Empty string 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, and similar in fashion. So list off some number of zeros followed by the same number of ones as the zeros. Can you tell me about what these strings, are they in the language or not? Yeah, they're all in the language. There are many other strings, but these ones certainly are in the language because they have the same number of zeros and ones. So, well, think about it. If we had a DFA, well, let's suppose we did have a DFA for this thing. Well, since it's a DFA, can it have infinite number of states? No, it has a finite number of states. Is the finite number fixed? Yeah, once I make the machine, am I allowed to put more states in if I want? No. So it has some number of states, but I don't know how many. Let's say it has m states. Well, let's suppose that what we tried to do was, let's feed these strings. We start with empty string, then we feed in 0, 1, then we feed 0, 0, 1, 1, and then we look at this DFA and see what it does. And if we suppose that whatever this DFA is actually does accept this language, then what should the DFA say on all these strings? It better say accept, right? If it actually exactly gets this language, right? It better not get anything wrong, right? Well, let's see. If it has m states, consider an input and its computation. What if I fed in a really long string? What has to happen eventually? Well, if I feed one of these strings, they better accept, but consider what would happen. What if I fed in a string that had m characters in it? It has to repeat a state. Why is that true? For a DFA with an input of length m, how many states does it see? M plus 1. How many states are in this DFA? M. So it has to repeat a state twice. Yeah.
Can you explain why it's M plus 1?
Right. So if we see 0 characters, how many states have we seen? If we see 1 character, how many states have we seen? 2. If we see m characters, how many states have we seen? M plus 1. Well, think about this input. 0, m, 1 to the m, and this exponent notation right here is equal to 0 m times. So 0 m's in a row followed by 1 m's in a row. Within those first m characters, what has to happen in this DFA with m states in it? But don't even consider the ones yet. Think about the zeros. What has to happen? There are m zeros, so what must happen? It has to repeat a state. So how could the DFA remember the number of zeros? It's not a valid argument, but it's just an intuitive argument. It can't remember the number of zeros because can the DFA remember information once it's processed some input? No. So how can it match the number of ones correctly? Because it can't see into the future. Seems like there's a problem, right? And it seems like I just assumed that this is an arbitrary DFA. I didn't assume anything about what it did. I just said it had to have some number of states, and it must say yes on that input 0 to the m, 1 to the m. But our intuitive argument says that can't possibly happen. So it seems like this language cannot possibly be regular because there's no DFA for it. Or it seems like there's no DFA for it. But we have not proven this. There could be some other way that does work. I'm not saying that there isn't a way, but we're going to now formally prove there is no way. Okay, but any questions on that intuitive argument? Sweet. Well, like we said before, we don't know anything about this DFA other than the fact that it is a valid DFA, so it has a start state, transition function, all that stuff. So let's say its start state is right here, and without loss of generality, let's say it has, actually I can't say without loss of generality, but let's say it has 3 states, for example. Well, let's see. If we try to feed this input into here, then what we noticed is that it had to end in a final state. Why does it have to end in a final state? Yeah, because we have to accept that input because it's in the language, right? So whatever happened, it must end, let's say, in that final state. It must end in one of them. And it must start in the in the start state. And I'm not saying that the start state's not final. Actually, it should be in this case, but I'm not saying anything about the start state. I'm not saying anything about the final states. They could all be the same state possibly. But I'm just making this as an artist's conception, as it's called. So it has to start in the start state. It has to end in the final state. But what had to happen in the middle? It had to repeat a state somewhere. It could have been the start state. It could have been some final state. It could be some state in the middle. So let's just make it arbitrary and say, let's say that this is the state it happens to repeat in the middle. Well, since it repeated, then there must be at least one transition starting from that middle state and eventually coming back to that same state. It could be one transition, maybe like a self loop or something, but it has to be at least one transition because we said it repeated and this thing is a DFA. There are no epsilon transitions. Okay? Do you need a minute to soak that in? Yeah. What? What part? All right. So, yeah.
So what you're saying is there has to be one state that it could have a self loop, or it could go to another state and then come back.
Yeah. There's at least one transition where it started at that state and eventually came back. Yeah, it could be a self loop, but it needs to be at least one because we said it repeated.
Squiggly arrow means like any
Yeah. So these squiggly arrows just mean a bunch, scientific term of transitions. So back to the question over here. So what are we trying to do? We're assuming that this black box DFA supposedly accepted this language has the same number of zeros and ones. So whatever input it gets, if that input has the same number of zeros and ones, it better say yes on it. And if it doesn't have the same number of zeros and ones, it better end in a non-final state, right? In order to get exactly that language. Well, if we try this input 0 to the m to 1 to the m right here, and the DFA has M states, then within the zeros part, it must repeat some state somewhere. Because we'll see M plus 1 states in this first part alone, in the run of zeros. And once we read the entire input, we must end in a final state because we must accept this input, 1 to the M. Okay, does that make sense? Okay, yeah.
So you're saying it has to repeat a state because before we've read any input, we've already seen a state?
Yeah, yeah. So if we've seen K characters, we've seen K plus 1 states. Or we've had a sequence of K plus 1 things. And by the pigeonhole principle, if we have K pigeonholes and K plus 1 pigeons, there must be some pigeonhole with 2 pigeons in it at least. Okay? Same thing here. If we have M characters read so far, the zeros part, and we have M states, we've seen M plus 1 states, and there are only M of them, so one of those states had to repeat at least once. Yeah.
Wouldn't that be bad for the pigeonhole principle? You have M inputs though.
What's there?
Aren't you saying you have M inputs
Uh,
and then M plus 1 states?
yeah. Yeah, so I'm trying to put the, we're executing M transitions of M plus 1 states. So it's putting states, it's putting characters to,
More states than you have here.
no, it's putting the states you see in the sequence to the states in the DFA. So like if we happen to see the sequence Q0, Q2, Q3, whatever, it's putting those, trying to match them up into the original DFA. Even if we see every single state, which we might not, but even if we see every one, there are M plus 1 things here.
Oh, so you have more inputs. Than
Yeah,
states.
we have not more inputs. We have more states in the sequence that we've visited, all the states that we've visited. Then we have states. Yes. I assume that because this DFA has to be fixed, because I can't arbitrarily add states. Yeah.
The plus 1, we're only saying that that's there
Yeah.
because no matter what, as soon as you start on your DFA,
Mhm. You must see
go to
one.
start state,
Yeah.
so that's automatically that plus 1, and then
Yeah.
M is like everything else after that.
Mhm.
So when I was saying inputs, I meant like inputs matching. This
Oh, yeah. Okay.
And so on this representation, the arrow pointing in, that would be
The start state. Yeah.
Count like that's the first one.
Yeah. So before we read anything, we've seen one state. Yeah. Other questions? This is good. Okay. Cool. Well, let's connect these arrows up. And I'm not saying at all that there's no other state that we've repeated. We could have repeated many states. We maybe repeated some state M over 2 times, let's say. I'm not saying that. I'm saying there is at least one state that's repeated. Okay? So, well, we had to read some string, some part of the input, in order to get from the start state to where that repeating state is. Right? We had to read some characters. It may be empty, but we read some characters. So let's call this part X. Well, then we got to name the other 2 pieces. So let's call the looping part Y and the last part Z. So the entire input concatenated together is X to get to the repeating state, Y to go back to the repeated state, and Z to the final state that we're supposed to go to. Okay, so the input in this case equals X, Y, Z. Let me ask you a question. Is XZ in the language?
Yes.
Yes. Why? Because why? Because what we can do is start state, read X to get to the repeated state, we don't have to take this looping part if the next character says we don't have to because it's a DFA. Then we read Z to go to the final state. So I don't have to take that Y part if the next character says go to where the Z part is. Okay? Let me ask you another question. Is X, Y, Y, Z in L? Yeah. How come that's true? Yeah, I can repeat that loop. I can have a string that repeats that loop twice. So this is kind of like our example of the 0 to the M, 1 to the M thing, where if we have M transitions of the 0 part, we came back to some state. But if I had more zeros, then I could have that part repeat again. Same thing here. Let's generalize this. Is X with I repeated copies of Y, Z, in L for all I at least 0? Yeah. What is Y to the 0? Y is not a number. What is the string chosen 0 times? Empty string. And did we cover the empty string case? Yeah, that was XZ from before. But if I is non-0, then we can just take that looping part I times and just take the X part before I times on the looping part and Z to go over to the final state. Okay? Sweet. And let me ask you another question. What do we know about Y, the repeated part? Is there some property that you can immediately tell me? Well, it's between these strings X and Z, but something about Y individually. Well, it comes back to the same state, but in terms of the actual string itself, is at least one character. Y is Y at least one character? Because it repeated a state because it's a DFA. It's not an NFA. If it was an NFA, then I could have an epsilon transition, which is a self loop. And then therefore Y could be empty or have 0 characters in it. But since it's a DFA, which are equivalent to NFAs, then it's either a self loop on a some character, in which case it's at least one character, or it's a sequence of transitions on some characters, at which point it has length at least 1. So we know that Y's length is at least 1. Or equivalently, Y is not the empty string. Yeah. Yeah, it's fine. Yeah, so yeah, this is the hardest part of the class for a lot of people. So it's good you're asking questions. So why is Y non-empty? Well, we made the string so long so that we must repeat a state. And we chose our X, Y, and Z so that Y was the string that we read from the repeated state back to the repeated state, because we said it repeated. But since it's a DFA, here's a more formal way to prove the exact same thing. So let's say that we have the computation going along, and then we have the state Q, which is the repeated state. Well, what is the closest place that Q could be after the original instance of Q? Because it's repeated. The very next one, right? That's the closest it possibly could be. How did we get from here to there? Via reading some character. How do we know we read some character? Well, we could have read nothing, could we? No, why? It's a DFA. Right. Because it's a DFA, we know we must have read some character to go over there to the repeated state, or see that state again. So that's why y is not empty. It's the string that is denoted to be from when we saw that state to when we saw it again, whatever we've read along the way. And it must be at least one character, because we saw it in the sequence, and because that's the DFA. Does that make sense? Okay.
Isn't this point that we're making now contradicting the point that we made just before you said that x, y to the I z exists in L for all I greater than or equal to 0?
Correct. A good point. X, y to the I, z is a different computation. It's not the same computation. And because it's a different string, because y is a non-empty string, x, y to the 1z, let's say, is different from x, y to the 2z. So therefore, they're different computations. And so therefore, this computation right here won't be the same if we stick in another y or take a y out. Yeah, because we'll definitely take out some of the computation of the machine. Okay, does that make sense?
So you're saying y to the I is a repetition of the y state?
Y is the string that you read from the repeated state back to the repeated state. And we're saying that we have that particular string repeated I times. Okay? Does that make sense? Yeah.
Why couldn't you just have y is greater than or equal to 1 instead of absolute 1, the absolute value of
The length of y. So
it?
vertical bars are length. Yeah. They're exactly the same thing. Either it's not the empty string or it has length at least one. Same thing. Other questions? Yeah.
So we kind of like forcing y to repeat. Is that essentially what
Forcing what to repeat?
y?
Well, why
Well, is that why y has to be
we
1?
we guarantee that the string is long enough, so there must be repetition. Yeah, there must be some repetition, and we're denoting the part that is the repeated part to be y. Yeah, we're just talking about some properties. So the key insight here is that once we have x, y, z, now what we're trying to do is reason about other strings in the language. So we're trying to, once we have x, y, z, we're trying to reason about x, y to the I, z. So the whole thing here is not only are we trying to figure out a possible language that's not regular, but another insight that you should see is that we can actually reason about, once we have some strings, we can reason about other strings in the same language. Like before, when we were talking about regular languages, we were talking about how to combine regular languages to get other regular languages. Here, what we're doing is we're trying to reason about, once we have strings within some language, we're going to talk about the same language but other strings in the same language. Okay? And so this is what we're trying to get at here. But any other questions otherwise? One more question I want to ask you. And we actually proved a very important result once we finished this. So how early can we guarantee the first repetition? Just learn to spell repetition. Of the input B. What's that?
Earliest repetition could be the initial.
Yeah, yeah.
Guarantee that, right?
What's that?
We can't guarantee that, right?
We can guarantee it after some amount of time.
Yeah, after the number after n. Right?
Exactly.
Yeah.
After M. After M characters. Okay? Or another way of saying that, once we've seen M characters, now we've guaranteed that a state must have repeated because of discussion earlier. But think about that for a second. What was the part that repeated? Why? Oh, So the end of y, how late could the first repetition be? M. That's the latest it could be. Oh, could the end of y be later than the mth character? No. Oh, what about x? Could that be later than the mth character? What about x and y together? That has length at most m. So it's a proof, so it's not a contradiction yet. xy has length at most m. Yeah.
Why is after m character is the answer to that question?
Because we guarantee that the first repetition occurs within the first m characters. Because we had to repeat a state by the mth character. So it could have been before, but by then we had to have seen the state twice.
So it's kind of like a constraint.
So this constraint is not actually strictly necessary, but it's extremely helpful. Yeah. Because we could reason about where the repetition could be anywhere else if we had a really long string, but if we restrict where the repeated part could be, then we can actually say a lot more, a lot easier. But it's actually not strictly necessary, yeah.
Would it be accurate if you said by the n minus 1 character? Because if the n character has to go to a final state.
The input I'm saying has length at least m. At least m. Well, if I have m minus 1 characters, how many states will I see in a computation? Exactly m. So it may be possible that I see exactly every state exactly once. And I wouldn't repeat. But if I have m, I must repeat one of them at least. Right? Does that make sense? Other questions? Cool. So we actually just proved a result that strikes the fear in many students across the world. It's called the pumping lemma for regular languages.
When is the fear settled?
Those first two words.
If you're not feeling fear yet, then you're
But
fearless.
But the key here is not what the lemma actually is going to say. The key here is the insight that you get when you realize that once you can reason about when you have long inputs that repeat states, now you can reason a lot about what other strings look like in the language, the structure of the language. So that's the key insight.
So I have a question.
Yeah.
You talked about the xy with relation to the m.
Mm-hmm.
I mean, why didn't we talk like just add z and just say m plus 1? Like xyz is less than or equal to m plus 1. Is that something that is helpful or just not helpful?
Well, z will actually not be very useful. We'll not actually need it in order to prove something's not regular or whatever. But we need something to get from the repeated state to the final state that it's supposed to go to. It could be the empty string, in which case the repeated state is the final state, which is entirely possible. And we need to account for that when we do proofs of this nature. We'll see examples, don't worry.
I was just thinking, is that a simple, easier way to get to like xyz is less than or equal to m plus 1 and then
We actually can't reason about what x, y, and z are. I'm saying that there is some decomposition that works, and we'll get to there. Yeah, I didn't say anything about what this repeated state is. It could be anywhere in the string. I'm just saying that there exists a string. There is some way to write the string w, or the input, as x, followed by y, followed by z. Okay, yeah.
If the repeated state is at m, is it just like z?
Well, the input will actually say needs to be of length at least the number of states. So we actually can't reason about the length unless we specify what the length is. But all we need to say is that it's at least the number of states. Okay? But if it happens to be of length exactly m, then, and even if we say that, then it could repeat the state way earlier in the computation. I'm saying that it repeats by then. It could be the very first transition could be the Y part, but I don't know where it is in general, because we're going to be assuming that a DFA exists for a to-be non-regular language, so we can't infer anything about the structure of the DFA. Okay, does that make sense? Other questions? All right, so let's basically just write down what we have been talking about. So let L be a regular language. And in the entire statement of this lemma, I'm not going to say the word DFA, I'm not going to say NFA, I'm not going to say regex. I'm just saying that there is this let L be any regular language. But in the back of your mind, what are you thinking right now? It has, it was in unison too. That was the 355 choir. All right, let's see. Cry. Yeah. Well, let's see. What did we have to guarantee about the input in order to guarantee there must repeat a state? At least the number of states. Well, if the language is regular, there is a DFA with a specified number of states, by definition, right? Because I assume that it is regular. So then there exists a supposedly called pumping constant. I'm going to call it P. It's also called in other contexts pumping length, but we're going to use pumping constant or just P here. And we say that P is for L. So without going back up, what do you think that this P constant is supposed to represent? The repetition, and that corresponds to the DFA in what way? The number of states. So in the back of my mind, I'm thinking that whatever DFA is for L has P states. It may have, we don't know anything about this P value, right? Because I didn't specify what regular language it is. But since it's regular, a DFA exists, and therefore this P is a positive integer, some positive integer. But we don't know anything about it. It's some constant. Okay? Well, remind me again. So let's say that this DFA has P states. How did we guarantee that the input repeated a state? It has to have at least what characters? P plus 1, or can we get away with P? P characters. So it has to have at least P characters. And what other property of the string, the input, do we need? Something to do with the little z thing at the end. It has to go to a final state, right? Because we're reasoning about strings in the language. I never reasoned anything about strings not in the language, okay? So we have to guarantee it has to be at least the number of states, or this P value, and has to be in the language. And is this true for every string in the language with length at least P? Yeah, because for every string in the language with length at least P, it looks like this, where you have to repeat a state and eventually go to the final state. Every string in the language with that property has that. So, so we have this pumping constant P for L, so that for all strings in the language with length of W at least P. Don't worry, there's more. But this is our intuitive idea. We need to have the string be long enough so that in the back of our mind, the DFA that we're thinking of, we repeated a state and we can go to a final state. Well, when I mentioned that there is some way to write this as X, Y, and Z, there's some way to write it, right? So let's write that. There exists a way to write W as X, Y, Z, so that, and then we have what are called the three famous conditions. Well, what's one of the things that we were able to reason about in terms of other strings in the language? Well, if we repeat that Y part as many times as I like, that's always in the language, right? So we have that X, Y to the I, Z is in L for all I at least 0. So all we're really talking about here is a language, and we're talking about the strings in that language. We're not mentioning anything about a DFA here, but we're thinking of a DFA. All right, well, what other properties do we know of this string were we able to deduce? Yeah, the length of Y is at least 1. And this is actually required. I could drop the third condition, but this second condition I must have. Well, what was the third condition that we were able to deduce? Yeah, X, Y has length at most P, right? That was the other condition that we were able to deduce. The place, so Y represents the first place that had a repetition. I'm not saying that there are other repetitions. There could definitely be other repetitions, but the first one I'm representing by Y. And so that XY has length at most P means the first repetition occurred within P characters. Okay? So that's the statement of the lemma. So let's recap. If we have a regular language, then there's a DFA with a certain number of states P, let's say, such that if you feed in strings that are long enough and eventually hit a final state, so they're in the language, then there's some way to write that string as a part that goes from the start state to whatever repeated state it is. Then, because we repeated a state, there's some sequence of transitions we did to go back to that state, and then some string that we read from the set of that repeated state to whatever final state we were supposed to go to. There's some way to write it. There are many ways to write the string W as X, Y, Z that satisfy these conditions. I'm saying that there is some way such that when you feed W into the DFA, it'll accept that string. Okay? Any questions? Yeah. Mm-hmm.
Magnitude or Y is greater or equal to
Mm-hmm.
1.
Mm-hmm.
And if the I equals to 0, so means the Y doesn't exist.
So
It's
you can answer, but this is probably the most asked question I've ever gotten about anything in 355. This one question about I is at least 0 and Y is at least 1. So go ahead if you had the answer.
It's because with I is 0, Y is 1.
So it's a great question. Let's think about it for a second. And then we'll take a break right after that. So if we had this repeated state, like this is X, this is Y, this is Z. If I from the first statement is 0, what is xy to the iz? Xz, because y chosen 0 times is the empty string. Does y still exist? Yes. Because if I put in copies of y in, then I'm going to make the string longer, in which case I'm going to go around this loop that already exists in the DFA more times. If I happen to choose I equals 0, that just means going around that loop 0 times.
So it's the accepting strings you should be considering.
Yes, we're only considering the strings in the language. I'm not saying anything about strings not.
So it's basically just saying the loop exists, we don't have to take it.
Not quite. The loop exists, but the string xz, because it's a DFA, will not take that loop. It's not the machine is not like choosing to not go around that loop. It's that the string mandates that it doesn't go around that loop. Okay? Other questions? Does that answer your question?
Yeah.
Okay. Other questions? Yeah.
It's kind of weird because does the state get repeated?
Mhm.
No, it doesn't go around.
Yeah. So I'm not guaranteeing that xz I equals 0. xz does not repeat does repeat a state or not. I'm not guaranteeing that. I'm guaranteeing that xyz repeats the state. But it can certainly be the case that xz doesn't. But that's not the only string I'm talking about. I'm talking about an infinite number of strings. Because I can go an arbitrary number amount of times around this loop. Okay? Does that answer your question? Other questions? So let's take a 5-minute break. Then when we come back, we're going to do a whole bunch of examples about proving some language is non-regular.
If someone emails